Hi sir, this is Tanmay from RGAKT Newsweek from CSE department and my domain is engineering physics. The topic I have chosen is EMI. So here what we discuss is definition, discovered by, experiments, observation, results or laws, and some few basic concepts. Okay, so before going into the main topic, first the basic concept is we all know that when there is a current carrying wire, it produces magnetic field around it. So what this concept means, here in the whole experiment he used magnetic field. So to produce magnetic field we can't use magnets lifelong. So what we use is we take a current carrying wire so that it produces magnetic field around it, which can be used for further examples and experiments. So the next basic concept is magnetic flux. Yes. So magnetic flux means number of field lines passing perpendicularly to surface area. Yeah. So what does that mean? Here we can see clearly that this magnetic flux is number of field lines. So magnetic flux means magnetic field lines, and it's denoted by phi B. B represents magnetic field and this phi represents the magnetic flux. So let's take an example. So here it's some surface and magnetic field lines are passing perpendicularly to this area. So the magnetic flux will be, number of field lines is 2. So magnetic flux is 2. Let's take the same surface and here we take strong magnetic field. So the number of field lines will get increased. The flux will be 1, 2, 3, 4, 5, 6. So the flux is 6. Let's take a large surface area. Here the number of field lines will get increased. So here the flux will be 3, 4, 5, 6, 7, 8, 9, 10. Based on these three diagrams, what we observe, this flux is directly proportional to the magnetic field. Here what we have taken? Strong magnetic field. Here what we have taken? More surface area. Now what we can say? This flux is directly proportional to magnetic field. If it's stronger, then the magnetic flux will be more. If it's weaker, then the magnetic flux will be low. In here, we can see that magnetic flux is directly proportional to the surface area. So if it's more, then the magnetic flux will be more. If the area is less, then the magnetic flux will be less. And one more thing is, if it's the surface area and instead of passing perpendicularly, if the magnetic field lines is making some area, making some angle with the perpendicular line, this is the perpendicular line, 90 degrees. Let's take that these magnetic field lines are making some angle called theta, then this angle will also takes effect in this magnetic flux. So what we can say, this magnetic flux is directly proportional to both magnetic fields and area and direction of the magnetic field line. dot product. So it can be represented as flux is equals to V A cos theta. Why cos theta? If this is making some theta angle to the perpendicular line, this will be V cos theta and this will be V sin theta. So here we are taking only perpendicular field lines. So what we take here? VA cos theta. These are the some basic concepts. Now let's go to experiments. This magnetic field like electromagnetic induction is discovered by Faraday. So what's the experiments he has done to discover this electromagnetic induction means? First thing is he took it first experiment. What he has taken is he has taken some steady magnetic field. This represents that it is coming outside of the board in Z axis. Okay. So now what he has placed a conductor in this steady magnetic field. But what he has observed is there is nothing changed. There is no change. Like there is no observation to observe. So what he has done is he has changed this magnetic field. That is, he increased it, decreased it, and observed. What he has observed is current got induced in this conductor. So while magnetic field is steady, no current got induced. But if it is changing, then current got induced. So in first experiment, current induced. Now with the same setup, he has done it differently. In second time, he again looks to the steady magnetic field and placed a conductor here. Now instead of changing this magnetic field, what he has changed is the radius of the conductor. So what will happen if we change the radius? The area of this conducting material will get changes. It shrinks or expands. So surprisingly, what he has seen is here also the current got induced. Okay, so we have seen both the things which is in the magnetic flux. When there is change in magnetic field, current got induced. When there is change in area, current got induced. Now he has done another experiment. Here also he has taken a steady magnetic field and a non-changing conductor. So the radius remains fixed and the magnetic field range is also fixed. So what he has done is he has connected it to some string and tried to rotate it. So what will happen? If this is the magnetic field, the angle will be changes. The area of this coil and the angle between area of this coil and the magnetic field direction will changes by theta. Surprisingly, here also he saw that current got induced in this coil. So what he stated is, if there is change in magnetic field, current will induce. If there is change in area, current will induce. If there is change in angle between magnetic field and area, there also current got induced. Based on these three experiments, he has stated two laws. Before going to the laws, let's discuss one more topic. Here, is current getting induced or potential getting induced? Current or potential? So, if we place a straight wire instead of this circuit, if we place a straight wire here, there what we can observe is the potential get induced in this connector. Then why we are seeing current means we can, if it's a closed circuit and if there is potential, then current get induced and it can be measured with some galvanometer. So based on these experiments, we can say that electromotive force get induced and because of that current will be seen. So laws of Faraday. First law. If there is change in magnetic flux, then the induced EMF can be seen in current. So what we need to do to see the induced current? Close the circuit to see induced current. So here, without changing magnetic field also, without changing magnetic flux also, the current got induced. So he changed the statement as, gave another form as, if there is relative motion between circuit and magnet. No need to change only magnetic flux, but also if there is relative motion between circuit and magnet, then also induced EMF can be seen. To see the current, close the circuit. To see induced current. Okay, so what's the next down we will get? How, what's the magnitude of this induced EMF? Like, if I get the magnet here and take it far away, what will be the change in the induced EMF? So, to answer this question, he also gave second one. Faraday's second law states the amount of induced EMF caused in the circuit. The magnitude of induced EMF is directly proportional to the rate of change of flux. So, if we take this symbol to represent induced EMF, then it is directly proportional to the, let's take some constant as 1, rate of change of flux. Rate is denoted by T and flux is denoted by phi. If it's RS, if we want some instantaneous induced EMF, then it can be taken as d phi by dt. This is how we can see the induced EMF and can measure the amount of induced EMF in a circuit. Thank you.